Thank you for that great introduction, and thank you to all the organizers for this. Is there a clicker? Oh, over here. Excellent. So before diving into the story of textiles and functional fabrics, a little bit of history. About 12 years ago, the US started something known as the Manufacturing USA Institutes, and AFFOA is one of these institutes. And these institutes are all about transitioning technologies that are being developed in academia into commercial markets to really get the US to go from being amazing in innovation and invention to amazing in manufacturing. There's about 18 institutes right now across different technology areas. All of them have something in common. They bring together the community of innovators, manufacturers, students, and so forth to really enable a manufacturing revolution in the US. So AFFOA, we got excited about textiles with one basic proposition that if we really want to reignite domestic manufacturing in textiles, we have to transform really what textiles really are. And our vision is to really combine microelectronics and advanced materials into the fiber and fabric manufacturing process to enable a whole new class of textiles, very different than what you know of today. Through the integration of these different technologies into the textile manufacturing process, you can enable a whole host of applications that many of you maybe never thought were even possible. So today I want to walk you through the journey of some of those applications and some of the things that we've done over the past 10 years of taking some technologies that are developed in academia and transitioning them into market. So there's three key kind of focus areas for AFFOA and really all the institutes. Number one is bringing together an ecosystem. It's not any one company that's specialized in this. What AFFOA does is brings together, again, academia, manufacturers, product companies, defense, Department of Defense, and other partners to really identify those opportunities and develop those products. The second thing is transitioning advanced technologies. We play a role of taking technologies from early stage when they're demonstrated in the lab and showing that they can be manufactured on production relevant equipment. And then the third area is creating the workforce of the future. It's really known that kind of manufacturing workforce is on the decline in the US, so we spend a lot of time in high schools and colleges really igniting excitement in advanced functional fabrics and what the future of manufacturing really looks like in this field. So as Roger mentioned, we're headquartered in Cambridge. We have an 18,000 square foot facility. It's a prototyping facility where we develop advanced fibers, fabrics, and full systems. I invite anyone to visit. It's a facility just across the river. But really what makes AFFOA special is the collaboration that we have with our members. We have about 140 plus members across 35 states in different areas. So when you look at this chart, you see that to really innovate in functional fabrics, you have to bring together a community with really disparate know-how. Traditional textile companies that are spinning yarns and making fabrics, advanced materials companies, innovative startups that have really great ideas for functional fabric devices but don't have connection to the manufacturing base. Academia is a big partner of ours. We have 20 plus universities, including Northeastern as a member. And we convene this ecosystem and we collaborate to advance the technology of advanced functional fabrics. So I wanted to kind of highlight, first of all, just a portfolio. There's a lot you can do with this. I'm not going to go through every example here, but this just gives you a sense of the types of applications that we've been recently pursuing, from healthcare to structural composites to Army uniforms with embedded sensors and communications. The portfolio is very, very broad, and every day we hear new ideas when people go through our facility. Oh my gosh, I never knew you could actually do that. Could you develop a product that could actually have this functionality in fabric? So we'll go through today, in today's presentation, just and you'll see a few examples of some of these technologies. So one of the first things that we did in 2016 when we launched the Institute, and we knew there's these pockets of innovation across academia, across startups, we launched a so-called project call. We said, come to us with your craziest ideas about transitioning functional fabrics into real products. And we actually launched 6 projects, and if you see, each project has something in common. They have an academic partner or a startup coupled with a manufacturer, all right? Because we knew that in order to get something out of the lab, you have to couple that technology onto the manufacturing floor. And what we showed through all these projects is within 1 to 2 years, get to a commercial relevant product. And I'll just show you one example that I thought might be interesting to everyone, which has to do with color changing apparel. This was a project that we found a University of Central Florida developing basically threads that can be electrically color changed. And they demonstrated hey, I can make a meter of this. I need a battery the size of a car battery to power it, but I can produce a color-changing fiber. Of course, the vision is full apparel, totally electrically color changeable with a smartphone. Imagine that. So we made a team, we partnered them with a yarn spinner, fabric producer, and made a small seed investment. And I want to show you the result of that just 1 year later through this video, which hopefully will play. There should be some audio here, please. Perfect. So pretty neat stuff. Pretty neat stuff. And actually, that technology, the team, thank you. The team that launched it actually just started a company a couple of years ago, and they're looking to commercialize this. And in fact, last year we also funded a project to look at basically automatic electrical connection to the wires in the fabric to really make it mass producible. So pretty revolutionary stuff. Another example here is a full fabric interface control. Imagine having a textile and basically a human-machine interface through a fabric. No hard components here at all. It's a textile that has only 2 electrical connections, but yet can determine the place that you touch it anywhere along its surface. So, which is really exciting. You can see here, you know, a piano keyboard being developed here. This is knit on a knitting machine, completely autonomously, no human in the loop here. Literally only 2 electrical connections, enabling you to identify at any point on the fabric that you're touching through simply capacitive and conductive yarns. Another really cool project that's recently we've done in collaboration with a small company called Python has to do with sensing really small ENG signals for musculoskeletal injury, for rehabilitation of those injuries. And here, there are sensors that can do that. Python has a wearable device that that you wear, and it picks up very tiny electrical signals. You can actually use it to control devices, like including drones. And the idea was, can we use that type of electrical device to pick up small electrical signals over a larger area of the body in order to understand how recovery is going post a musculoskeletal injury? So long story short, we partnered with them and figured out how to actually integrate those devices and those sensors onto a fabric and develop a full prototype system that we can now scale up to produce a full wearable ENG sensor that you put onto your body and actually has the distributed sensing onto it. And again, these things, you know, picture is worth 1,000 words. A video is even more, you know, impressive in terms of how it's made. So I wanted to just show you how that comes together in terms of bringing together the electronics and the textiles in a seamless way. These are actually soft electrodes, fully conductive, fully soft, no hard objects there. These are conductive threads for power and data. So we literally recently completed about 20 prototypes. We're giving these to the Army now to test for soldiers that are coming back that are injured and seeing how this device will help actually accelerate their recovery back to service. Another quick example, again, problem motivated by one of our military sponsors. How do you detect the onset of hypoxia, the drop of blood oxygen level in someone who's going to jump out of an airplane. This is a big, big deal. People whose oxygen level drops, they may not even feel it until it's too late. Here we developed essentially a headband that goes underneath a helmet that's measuring your blood oxygen level and sensing that and sending that data to the commander so that they know exactly the physiological status of all their troops in the aircraft before they jump out. So those are all cool examples, all right? And what I want to transition to now is a really interesting technology that's yet to be fully commercial, but that we've been working on for about a little more than 10 years, that actually involves building the microelectronics and those sensing capabilities directly into the fiber itself, not on top of the fabric, but into the fiber. So here's a cross-section, essentially, of a regular thread. So if you take your t-shirt and look at a cross-section of a fiber, it's a single material entity, polymer. What we're going to be talking about right now are multi-material fiber microsystems. These are fibers that are engineered to actually have really sophisticated functionality at the fiber level. So what we're talking about is integrating semiconductors, insulators, and metals, all with very precise geometry, into a single thread that can actually be woven, knit, and treated like a regular textile. This is really the future of advanced functional fabrics. And the way this process works, I actually brought a couple of demos. Is you start with building a preform, some object like this. Believe it or not, this object contains all the ingredients that you need in the fiber, but it's not yet a fiber, it's a preform. And then you put it on a furnace in a tall draw tower, and you heat it and you pull it. And essentially you go from that preform into kilometers of fiber that has the same cross-section as the preform. And through that approach, you can create a wide range of cross-sections and a wide range of functionalities. You can create fiber structures with unique coloration properties. You can even introduce a whole host of sensing capabilities, including thermal, acoustic, optical, and chemical detection in the fiber. You can go the other way, where you can actually put power into the fiber and create all sorts of excitations, including optical, acoustic, and others. And you can even engineer the surface of the fiber. So I want to walk you through a little bit of the journey of how you produce these things, because it's, in many cases, if you study material science, it seems like it's impossible. How are you going to produce a fiber like this? And the very first idea actually dates back to the 1970s. There was a concept of, hey, can I make an optical fiber where I guide light not through a glass or through any solid material, but through air? Because of course, air has no loss. You know, if you want to guide light through glass, it's maybe good at 1.5 microns, but what about at 10 microns where there's a CO2 laser wavelength is going to be highly absorptive? So this notion of creating a hollow core waveguide has been around for decades, and it really wasn't until early 2000s that it was actually realized. And the reason is, well, you need materials of two different refractive index to act as a mirror, right? If you have those two different refractive index, and if you could draw them together, you can create such a fiber structure. Well, if you do that, you know, typically this is what happens. You're not going to find materials that can actually co-draw. And in fact, in the early 2000s, there was publications in Science and journals like that that would say, there's no way you can actually identify two materials that have disparate optical properties or disparate electrical properties, but have compatible thermomechanical properties that they could be co-drawn. Because that's kind of what it takes. If you think about this process, if you have this preform and I put it in a furnace and I draw it, I mean, you're applying a stress to this fiber. So all the materials actually have to flow at a common temperature. So for those that are studying material science, you might be familiar with this viscosity versus temperature curve. And the only way you're going to have the materials flow at the same temperature is if they have an overlapping viscosity in that temperature range. And so what we did is, this is actually work that was done early on at MIT, even before AFFOA was stood up in the early 2000s, was in fact, materials were identified that fit this criteria. Of course, taking into account this time constant here, which when you have fluids flowing, what happens if you turn on your sink, for example, and you watch the water come down? Eventually, it's going to start to go from a cylinder into spheres. Essentially, the surface tension will come over, and you're going to have capillary instability. And the timeline associated with that capillary instability has to do with the feature size, the viscosity, and the surface tension. So the trick here is draw your fiber in a time scale that's shorter than that capillary instability. So you preserve your geometry and preserve your cross sections before physics takes over and surface energy starts to take over and you lose, and all bets are off at that point. So we did that, and essentially you could see the kind of structures you can create here. These are high and low refractive index materials drawn in a fiber. You can start to control the wavelength of propagation from the UV all the way to long wave infrared. You could use this for light guiding, and a company was started, in fact, called OmniGuide. The first minimally invasive surgery was performed with these fibers for guiding light through the hollow core, actually CO2 laser light. But also you can create external reflecting fibers. So you see the different colors on the bottom right. Those different colors are not made through any pigments or dyes. It's the same materials. It's just different length scales, right? The smaller the materials are, the thinner they are, you push the reflectivity over to the lower wavelengths, to the UV. So this is really cool, but we're at a sensors meeting. So for sensors, you kind of need another ingredient. You need a metal, right? You need a metal to get some electrons out. So how are you going to do that? How are you going to introduce a metal into this whole game? Well, a metal is different than these other materials in that it is crystalline. So a metal on this graph is going to have a really sharp drop in viscosity at its melting point, right? So it doesn't have a gradual change in viscosity, so it melts. So how are you going to introduce a metal into this process? So the scientists back at MIT in 2004 developed a process to do that. In fact, carving out a couple of pockets for metal electrodes, putting those electrodes in, these are low melting temperature metals, but encapsulating them in high viscosity boundaries using the polymer as a high viscous material that allows you, in fact, to go from, you can see on the left-hand side here, the preform design. There's a semiconductor core. The semiconductor, basically, if you shine light on it, it would generate an electron-hole pair, and those metals would pick up that electrical signal. And you can see the cross-section at the preform at about 3 centimeters in diameter, and the cross-section on the fiber, it's identical. The structure didn't change. And so just to show you what that looks like, again, at the single fiber level, you have this curve on the bottom right. If you connect those two electrodes to a voltage, to a power source, and you can measure the current as a function of illumination, and you have a simple one-dimensional photodetector. And why that's kind of cool is now you can start to look at kind of large area sensing systems using such fibers. So here's an example of a grid, 30 by 30 fibers on these two grids that could reconstruct essentially illumination through that grid of light. And this work actually moved on over the past decade or so. There's even lensless imaging systems that were developed using this technology. Again, no lenses or anything, but just a large area fiber system to do sensing and even optical imaging. For those who really want to nerd out about this, you could actually create a spectrometer in a fiber. So this was developed essentially taking this capability, creating these semiconductors to be very, very thin, creating multiple layers of these semiconductors. So this cross-section of this fiber here, in fact, can detect not only that light is illuminating it, but it can reconstruct the wavelength of illumination, because you have absorption in the first layer, and then you have the absorption in the second layer, and the ratio of those absorptions will give you, or is a unique function of the wavelength, which is pretty neat. You can also replace the semiconductor with one that is has a temperature-dependent conductivity to start creating temperature sensing fibers and fabrics. Really, the sky's the limit here. There's a whole host of materials you can start to integrate to create large area sensing systems. We moved on a few years ago to show that we could actually introduce, this is in collaboration with E-Ink, a low power color changing solution. So you saw previous color change, which was really exciting. That was a thermochromic technology. So that requires you to kind of heat up the fiber, which is pretty power intensive. This is based on Kindle technology, the same stuff that you use in your Kindle, E-Ink technology, very low power, capacitive-based color change, where we're introducing these E-Ink materials into the fiber, and we're switching their color. And you can see in this video how the fiber went from black to white, and recently there's a full color gamut now that we're able to do. So that's really exciting, but we realized a few years ago that there's a limitation to having all the materials flow, because you might have semiconductor devices that don't flow at 200 or 300 degrees Celsius. And actual traditional semiconductors like silicon, there's no way they're going to flow. at that temperature. So the question is, can you actually do something clever? Can you figure out a way to incorporate traditional semiconductor chips into this fiber draw process? And that's what we did back a few years ago, again, primarily at MIT, and then we transitioned this to AFFOA where we scaled this up. And here we also start with a preform process, but we start to actually introduce the microelectronic chips into the preform, okay? They come together, and then during the draw process, we're introducing metal microwires. And believe it or not, as the preform converges into the fiber, those metal microwires make contact to the chip. And now you actually have a fully packaged microelectronic system in a fiber. There's one LED on the bottom that you can see there being contacted by the two wires. You can see a full spool of these here that's come out of a fiber draw. You typically get 300, 400 meters from a single draw. You can weave these, you can introduce, you can make them very, very small, et cetera. And again, LED is just an example. I'll show you more sophisticated examples in a moment, but this is a 2-terminal device with just 2 wires, just to show you the basic concept of being able to introduce conventional semiconductor chips into a fiber, where now you can really think about the fiber as a packaging platform for microelectronics. So one exciting application for this that we've been developing over the past few years in collaboration with MIT Lincoln Lab is doing large area sensing in the ocean. There's a lot of interest in the scientific community to map out temperature, salinity, and other excitations in the ocean. There's a pathway here to do that ubiquitously in a really cheap way. So we've started with temperature. We've introduced tiny temperature sensors along this fiber. We've deployed it in the ocean. You can actually see the real data here over about 90 meters, where from a single readout at the end of the fiber, we get a snapshot of the temperature profile of that fiber. And in fact, by introducing small IMUs into the fiber, we can actually reconstruct exactly the position we know exactly where every single sensor is in that rope. We know exactly its depth and position X, Y, and Z along the water column. Again, really exciting platform for technology development for additional capabilities in the future. Maybe the last example, which is a recent program that we're doing also in collaboration with Lincoln Lab, and there's many industry partners participating in this, has an interesting title called Smarty Pants, Smart Electrically Powered and Networked Textile Systems. This is actually the largest, probably, electronic textile program funded in the history of the US. This is funded by IARPA, the Intelligence Advanced Research Projects Agency. We're serving kind of as a test and evaluation group to develop standards for testing e-textiles. Now that this is kind of really taken off and companies are developing products that have embedded electronics into fabrics, what's the testing protocol? How do you evaluate comfort? How do you evaluate breathability, washability, abrasion, all the things you want to have in a garment? So the goal of this program is to develop a garment that can essentially do video recording, do audio recording, and do geolocation, all within a full wearable, all that has to pass what's called the basic comfort test. And so there's about 4 teams across the US working on this right now. And again, we're developing AFFOA, and in collaboration with Lincoln Lab, is developing the testing evaluation protocols to make this, to evaluate those systems. We're also developing a baseline system based on the technology that I showed earlier with the fibers that have the sensors inside of them. So again, it's going to be completely washable. It's going to be almost undetectable in terms of these technologies built into the textiles. And I think the last example I'll show you is I'll play this video. It's a technology that we developed in-house. The idea was we want to develop an e-textile platform that enables other innovators in the space to basically design into, such that if you have an idea, a new concept, you have a new sensor, you don't have to start from scratch. You have a platform you can basically plug and play into our system. So we called it originally Stem Cell. Now we redefined it as a universal development platform, but it enables you to basically look at a whole range of sensors within textiles. And you'll see a quick video of that. So with that, just to quickly summarize, AFFOA, Advanced Functional Fabrics of America, we look to accelerate the development and commercialization of advanced functional fibers and fabrics. We work with a membership network. It's about 140 members across the whole country. And we're really engaging on this multi-material fiber manufacturing technology that I showed you that has really promise for a whole range of applications in sensing and others. And welcome anyone again to visit AFFOA. If you have ideas, if you're working in this space, we'd love to chat. Thank you very much.